Okay. Very, very quick summary of what we did last Monday. It's just an introduction to the finite element method. So basically what we are doing here in this module is solving problems in engineering that are governed by these partial differential equations. Okay? In this case, what we have in here is this equation, which is nothing but equilibrium of forces, okay, for an elastic bar. We have then the material, we have the definition of the strain, and important, don't forget, we have boundary conditions, two types of boundary conditions. Could be Dirichlet, that means displacement known, or could be Neumann, that means traction, you've got known at one of the ends. The first thing we did is we spent a bit of time going up to what is called the weak form, right? Which is nothing but an equivalent form of the original equation. But now you have it in integral form. We apply the integration by parts in order to be able to use our boundary information. Okay, these are the two things to remember. And then we say, look, we are going to try to find a particular approximation of the solution. The simplest thing we could do is subdivide the bar in elements. In each element, use a linear approximation. That means that you are combining these piecewise linear functions, these hats. And the only thing I'm saying is that we are going to look for an approximation of this form, where the ends are these hat functions in there, and now the objective is to find the coefficients Q, numbers. So instead of finding a displacement field, a displacement function, we are after numbers, and everything looks a bit easier now. We insert these expressions into the weak form, and after some manipulations, we arrived to this equation in here, okay, where, very, very important again, on the left-hand side is what is unknown, that is the coefficient only, and on the right-hand side is what is known, which is an external force and boundary conditions. Yeah? And I think that was the last slide of last Monday. Okay? The actual system of equations. And I said we need to talk a bit about the Dirichlet boundary because we haven't accounted for the information known on the left part of the bar, okay, which is this Q1 is actually known in this problem. It's a given displacement at the left end. Okay? Clear? Questions? Nope. So just a couple of minutes to summarize what we did. Right. At the end then, when you are given a finite element problem, what you need to do is to build this matrix, build the right-hand side, and solve the system. This is typical procedure. We are going to be doing this for the whole course, okay, for different problems. It's always the same. Now, how do you compute this matrix on the right-hand side? You need to compute the integrals, right? And one thing that is very important is, yeah, they are integrals in the whole length of the bar, from 0 to L. Okay, the same for the F here. I'll be pointing here on the screen. So from 0 to L and from 0 to L. But these shape functions are very particular. These shape functions, these ends, are very peculiar, isn't it? Because you pick up one, and it's almost 0 everywhere, except in a small region. So we are going to use this information to avoid wasting time and doing silly operations, okay? Because the ends are almost 0 everywhere except in a region. Question for you now. If you look at one element in your mesh, how many shape functions are not 0 in an element? And this picture should help. In one element, how many shape functions are not 0? 1? More? More answers? 1? People is agreeing with you. Anyone disagreeing? No? Everybody agrees? I don't agree. So 3. 3. Okay, we got another answer now. Who said 3? Right? Any more? I'm taking all the answers today. 2, okay. Right. Look at one element. One element is, for example, in between node, let's go here, because the nodes have a number. Between node 2 and node 3. I can even plot it, if it's going to be easier to visualize. So I have my mesh, I have some nodes, right? And I have, remember, for each one of the nodes, I have one shape function, okay? Like that. This is N2. This is N1. This is, and I'm going to stop in here, N3. And the only thing I'm saying is focus in one element. That means, for example, this element here, forget about this, forget about that. How many do we have? Clear now? Yes. That's what you need to do in your head, okay? In order to answer this question. Does it make sense? 2. Okay, perfect. Here, there you go. So 2. So we are going to use this information, okay? This is just to say, this slide in here is just to basically tell you what I said already, which is N is 0 everywhere on the left, 0 everywhere on the right, and only in a small region is non-zero, okay? And for that reason, what I just said is let's focus in one element, and what happens in one element, you have two shape functions that are not 0. The one associated to the node on the left, the one in green, and the one associated to the node on the right, the one in orange. These are the two shape functions. First thing we're going to do, we're going to find them. We're going to find the formula, the expression of these shape functions. How do you do that? How do you do it? If I tell you, give me the expression, give me the formula of N1. What do you know about the shape function? You only know one thing. You and me and everybody else in the world. Only one thing you know about the shape functions. Which is? Linear. Sorry? It's linear. Linear, okay, you know two things. It's linear, I completely agree with you.
Inverses?
Inverses, what do you mean by inverses?
One of them is a positive gradient, the other is a negative gradient.
Yeah, but this is a consequence of what we know. This is a consequence. Yes, it's 1 in one node and it's 0 in the rest of the nodes. That's, put it in your head, okay? You're going to be asking the same question all the time. It's 1 in one node, in the node that is associated, 0 in the rest of the nodes. Right. Let's do this. So I have one element. I'm going to name the nodes x1e, x2e. The e that goes on the top as a superindex means that we are talking about one element. Could be element number 1, could be element number 2. It's a generic one. So it's a generic element e. And now, I'm going to plot this shape function here. Goes from 1 here to 0 here. That's the only thing we know, okay? So N1, I'm going to use the same notation, capital. How do you build it? Well, we've got the two things that we knew about this shape function is it's going to be 1 in the node x1 and 0 in the node x2. The easiest thing to do is to say it's going to be something like that, x2 minus x. Because if I insert x equals to x2, this will cancel. Agree? If I insert here x2, I will be doing 0. And that's a condition. It's one of the conditions I wanted, that the shape function takes value 0 at x2. Okay, but now, if I insert x1 here, I want this to take value 1, correct? So I scale it. I divide by x2 minus x1. And that's it. I just build a shape function that satisfies the 2 conditions I need. Do you agree? Yeah? Perfect. This one, x2 minus x1, is what? Is the length, correct? Is the length of the element. We are going to call it L. And the shape function will simply be x2 minus x divided by the length. And once you know how to do one, that's it. The other one is quite simple. And 2 will be x minus x1. This will cancel now when x is equals to x1. And to make it 1 at the other end, you scale it again. Okay, so that would be the final expression. That's a simple way to build them. Okay, you don't need to. Only thing you need to remember is that it's 1 in one node, 0 in the other node. That's it. Right. And moving from this to here again. I'm switching all the time. I'm switching all the time these screens because the only one that is recorded is the one on the side, remember, okay? So this is why I need to keep removing my handwritten notes. Anyway, you got n1 and 2. You can differentiate them, okay? You can differentiate, that's a trivial thing to do. Derivative with respect to x, and you will have one with negative slope, as you were saying, and one with positive slope, 1 divided by L. Negative and positive, just taking derivative of the shape function. Yeah, nothing spectacular here. And why am I doing these derivatives? Because I need both the shape functions and its derivatives, because the stiffness matrix contains derivatives, and the right-hand side contains the shape function without the derivatives. Right? So this is why I need these quantities. And now what we do from a practical point of view is, in order to build your stiffness matrix, you're going to compute integrals in an element only. Okay? Look that I'm changing here slightly. Okay? This is Kij, so this is the term Ij of your matrix, but with a superindex E. And that means that I am integrating in one element only. In contrast to, if I go back, in contrast to what we had before, where the K didn't have any superindex because we were integrating in the whole bar. Right? So now we have split the bar in elements, we compute these integrals in each element, and we assemble the global matrix. Right? So, as an example, we are going to do examples today, but because I think that at the end of the day, all this assembly, all this process is better understood when you do an example. But what I'm saying is, if you have your bar with, let's say, 2 elements, element number 1, element number 2, what we are going to do is, for element number 1, we are going to compute one stiffness matrix, which is going to be a matrix of 2 by 2, because you have 2 nodes in an element. Okay? For element number 2, you will compute another stiffness matrix, which will be 2 by 2, again. How big is the global stiffness matrix, K, without indexes? How big is this matrix? 3 by 3, because we have 3 nodes total in the mesh. Okay? And remember, we need to find one coefficient per node. So this is why the global matrix will be 3 by 3. So it will be a matrix like that. Okay? And now, what we are going to use is the numbering. This is the first element, so the indexes are 1, I don't want to use a circle here, 1 and 2. These are the indexes for the first elemental matrix. And the indexes for the second are 2 and 3. 2 and 3. Okay? And this is what you use in order to send this contribution to the global matrix. Here, in the positions 1, 2, is where you will send the contribution from the first element, because the first element has nodes 1 and 2. And then, in the positions 2 and 3, is where you will send the contribution from the second element. Okay? And as I said, we're going to do an example. This is just a graphic illustration of how we're going to solve the problems. Going element by element, building these elemental matrices, and doing the assembly. Right? Why do we have, maybe it's all trivial what I'm saying today, but bear with me. Why do we have this region here, the position 2, 2, where 2 elements are contributing?
Because there'd be a contribution from 2 elements on the same node.
Exactly, because node number 2 has 2 elements on both sides, okay? Whereas nodes number 1 and 3, they are in their own, okay? They are the ends. Right, and graphically, this is how it looks. The expression is what you have here in the slide. So you have the first element goes here, okay, the superindex 1. The second element will go here. You have the red elements highlighting contribution from 2 sides, and then you go on and on. Element number 3, blah, 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 up to element number n. And the same idea applies to the right-hand side. In this case, what you compute is vectors of dimension 2, and you assemble them together, and there is an overlap. Because, again, node number 2 is containing 2 elements, node number 3, and so on. Make sense? Yeah. Okay. Let's go down to the particulars now, because we are going to solve problems. The first thing I'm going to do is have a look at these elemental matrices. Have a look at these expressions in here. Can I get some numbers? Can I pre-compute things? And the answer is going to be yes. And let's do it then for a linear element. Okay, so let's consider a linear element, again, with any coordinates. You have your shape functions. We just built them before. So they are here. And one we said is x2 minus x divided by L. That means that the derivative is simply minus 1 divided by L. And n2, similar stuff. X minus x1 divided by L, and the derivative 1 divided by L positive. Okay? Now, the question is, what is the expression of the elemental matrix for one element with generic coordinates? Because then we can use it in exercises. We can program it, which is what we are also after here. Okay, so for example, K11. We said this is a 2 by 2 matrix. What I want to find is the entries of this matrix. So I'll start with the entry 1, 1. And this is nothing but the integral, according to my slide, A, or E first, if you like, jump modulus, area of the cross-section of the bar, dn1 dx, dn1 dx again. I need to compute this integral. Okay? First thing I'm going to do, Well, I'm going to assume here, this is an assumption, and actually E and A constant. Let's write it. Constant. Okay, it's an assumption. And I believe that if you've done finite elements before, you always assume that, right? Well, that's something that we are going to do this week, but we are going to stop doing. From next week, and this is when you start something new with respect to what you've seen before. Okay? This is a very strong assumption in general, to assume that maybe the material is okay, but the area of the cross-section, even the first exercise of the list that I'm going to do today, the area of the cross-section is not even constant. Okay? So it was a very, very strong assumption that you did to level 3 if you solve finite elements. The objective here is going to be to push all these limitations and go beyond. Okay? But for the moment, let's assume that. That means that I can take them out of the integral. That's why it's assumed, normally. And then I have the integral of what? Well, I can introduce the expression here of the derivative of the shape function is 1 divided by L, so I have 1 divided, let's use the same color, 1 divided by L E squared, which, by the way, is constant also, the length. The length of the element is a number, okay? So I can take it out. And I have EA L squared, the integral of this. So, question is, what is this integral then? What is this integral? The length, correct. Okay. This is nothing but the length. So one of the lengths cancel, and I have my expression, EA divided by the length. Agree? If not, tell me if there is something that you don't see. Clear? Right. Can you very, very quickly, I'm not going to do, in principle, we need to do 4 integrals, okay? Because remember, what we just did is to find this guy here that goes in this position of my stiffness matrix, the position 1, 1, right? Now I need to do the position 1, 2, and then 2, 1, and then 2, 2, right? So 4. But that becomes trivial. Can you straight away, someone, tell me the result of this one, if we follow the same procedure? Straight away. The same with a minus. Why? Because, let me point here. This assumption is still going to be done. This assumption here is still going to be done, so we do the same step. And then inside the integral here, you have 1 divided by L squared. 1 divided by L squared, because we are multiplying this guy twice. We are multiplying this guy here twice. In the second position, 1, 2, you need to multiply one derivative of the shape function by the other derivative of the shape function to compute this guy. So you have minus multiplied by plus. This minus multiplied by this plus. Yeah? So the only thing that changes is the sign. So that's minus A. 2, 1. 2, 1? Minus. Actually, what you should realize is that this matrix must be symmetric. It must be, by its definition here. Okay? If you change I and j's, what you're doing is change these two guys. You're changing nothing. The order of the product doesn't matter. So you need to use that when you do exercises, because that means that you can save time. Right? You don't need to compute the 4 terms of the matrix. You don't need to compute these 4. Actually, you need to compute 3 only. This symmetry, you use it to speed up and to check the results also. Okay? And then 2, 2 is equals to someone? EA positive, the same as the first. Okay. Is it clear how you get that? That means that we have found an expression for the stiffness elemental matrix of a linear element. You have a formula, okay? And then when you solve exercises, you don't need to go back and compute these integrals. You can use directly these expressions. If what? What is the assumption that we've made? I put it in red there, okay? So if you have a problem with constant jump modulus and constant area of the cross-section, just go, use this formula, full stop. Okay? This is why it's useful to get these formulas, because you can go also and program it. And any program that you find on the market, they have these formulas programmed by someone behind. Okay? Make sense? Yeah? Okay. Right-hand side. Right-hand side is this guy here. This is F, which is the external force, but unit length, multiplied by one shape function. So, let's have a look at this guy. Right. F, capital F, as in the notes. F1. So the first component of this vector. This is an integral, just copying what you have here in the slides, from x1 to x2 of F, small f is the external force, multiplied by n1. What am I going to do now? Well, I'm going to assume F is constant. Okay, just to get a formula, just to get a feeling of how things work. And then we will do it more complex next week. Or actually on Thursday. Right, so I got F going out, and I'm going to call it F of the element. Okay? F of this element. And the only thing that remains inside is the shape function, which I got it here, x2 minus x divided by L. And that's what we need to integrate. Okay? Now it's a matter of doing it. So L goes out. L is a number, remember, it's a length, nothing to do here. But you need to compute an integral now. It's not as simple as the one that we just did for the stiffness, which is in orange here on top. Okay, it's not as simple as this one. Why? Because actually the stiffness at the end of the day are derivatives, so the expressions are simpler. The expression of a derivative is very simple. It's the slope of this line, so it's a number, it's constant. Whereas the shape function is a bit more complex. It's not constant, you cannot take it out of the integral. So you actually need to do it. So let's do it. This is x2 multiplied by x minus x squared divided by 2, and this is in between x1 and x2. Okay, that's the integral of what remained inside. Happy with that? We are going to do a lot of integrals. I mean, in finite elements, because you start with a weak form, yeah, and it's an integral form, you always end up doing integrals. So if you need a bit of practice, get on with it, because we're going to do a few, right? And now it's a matter of rearranging things, just to make it look a bit pretty, nothing else. So that is the function that we have evaluated at the top, which is x2, minus the same function, x2 first, evaluated at the bottom. And make sure that I don't do mistakes, okay? That's something like that. Double check. Agree? Yeah? And I don't know, I'm pretty sure that we can get a better expression. Let's play a bit and see if we see something. This is x2 squared minus half, okay? So it's simply x2 squared divided by 2. And then we have minus x2 x1 minus x1 squared divided by 2. Just rearranging, okay, stuff. And I don't know, I can see here something, for example, if I take the 2 out as a common factor, so here, that would mean that it disappears from here, and you got a 2 here. And I can see that this is x2 minus x1 all squared. Agree? And this is nothing but the length squared. And now it looks much nicer. That is simply the expression you get. Yeah? A lot of, someone enters this room, looks at this screen, and it looks like we are doing here something really complex, but it's just an integral at the end of the day. Right? Happy? Yeah. Okay. This is for F1. You can do F2. But it's going to be exactly the same result. And at the end, what I just done is to do for you how to obtain these formulas here. Very, very important, okay? When you apply these formulas for doing an exercise, you need to make sure that the assumptions are valid. And the assumptions are here that these guys are constant, the modulus, area of the cross-section, and the force is also constant. Right? Question, quick one, to see if you're following. Do I need the force to be constant across the whole bar in order to be able to apply these formulas? Is that what I'm saying? When I say here that in order to take f out of the integral, I need constant force, constant external force. Is this across the whole bar? If not, just in the element. Okay, important. You can have in different areas different forces, and still this is valid. So it's a limitation, but make sure that you understand it. Right. So we have the stiffness matrix here on top for a linear element with 2 nodes. You can also write it, and actually it's going to be handy in some examples, to write it in this form. It's exactly the same as we had here, but written in this form. Is Young modulus, area of the cross-section, length, and then this matrix B, and I'm calling it a matrix on purpose, despite for this problem is a vector that contains the derivatives of the shape functions. Right? I'm calling it a matrix because if you go to any book, they call it a matrix because in 2D and 3D, which is what you are aiming for, is a matrix, not a vector. 1D, you only do 1D here in the class because you're learning, but in reality, 1D problems are not of interest, right? So sometimes it's useful to do it this way, to write the stiffness matrix this way. Why? Because this B has got a meaning. Right, let's go here. This B matrix that appears there in the slides, let's see what is the point of it. It says that it contains the derivative of the shape function. So basically, You take the derivatives of the two shape functions and you put them in a vector. So what's the deal here? Well, the deal is that if you remember how the strain is computed, strain is the derivative of the displacement, and the displacement, we are approximating it in one element as, I'm going to use the same letters as I use in the slides, otherwise, it's a linear combination. I'm talking about one element only now, okay? In one element I only have two shape functions, so displacement is just a combination of one coefficient, one shape function, plus another coefficient, another shape function. If I do that, the derivative of the displacement is the coefficient, derivative of the first shape function plus coefficient, derivative of the second shape function. And I can write this as scalar product of this vector multiplied by the vector of coefficients. Okay? Scalar product, first component by first component plus second component by second component. All triviality what I'm saying, okay? But the thing is, here is your matrix B. Right? This is why we like to introduce the B. The B has a very strong meaning. You multiply this matrix by displacements, Q contains displacements at nodes, it gives you back strains. So it's the matrix, and this is why it's called the strain displacement matrix. It transforms displacements into strains. Right? And then if you multiply the strain by the Young modulus, what you get is stress. Right? Yeah? Okay. No questions? Nothing? Okay. What else? Point loads. Well, that's just for completeness, I would say. This is the system of equations that you would get in general, up to F small plus capital F. F small accounts for the boundary, okay? Accounts for the boundary, so it looks like that. If you know a Dirichlet boundary condition, what you have is a reaction there. And if you know the traction, you put it there in this vector. Okay? Capital F accounts for external forces. I'm just splitting the right-hand side just to understand it a bit better. Okay? It's a contribution from the boundary, the small f I call it. It's a contribution here from the external forces, I call it capital F. And the only thing I'm saying here is that you might have also a point where you add a point load. Okay? And if this is the case, you have an extra contribution here, a P, right? And P is a vector that is going to be almost zero everywhere, except if you have at one point a point load. It will contain this number. Make sense? Example, you're looking at me like, what are you talking about? Let's look at an example which I'm going to revisit in a second. Imagine that you have two elements only, 3 nodes, and I have 0 displacement imposed in here, 0 displacement imposed in here also, right? But I have in the center point a point load. Yeah? Going back, what do I have? Well, my capital F is 0 because there are no external forces. There is no gravity, let's say. There is no gravity here. The small f will contain 2 reactions at node number 1 and node number 3 because you are forcing them to be fixed, so there will be a reaction force. And the P will be 0, the point load, and 0. The point load is, let's go here, the point load is 200 or 0.2 meganewton. So after the change of unit, this is what you have. No point load on the first node, no point load on the second node, sorry, on the third, but a point load on the second. Okay. So you can have in the most complex, I'm trying to be very generic here, in the most complex case, you will have the right-hand side built of 3 contributions: boundary conditions, external forces, and point loads. Right? Make sense? I think with exercises, all of that, plenty of letters here, when we start doing some actual problems, will be a bit better. Only one thing left before we actually can face some problems. I need to tell you, how do you handle there is a boundary condition, the imposed displacement boundary condition. We don't know how to do this yet. We've been ignoring this all the time. If you remember, and if you don't remember, I'm going back. Here, when we deduced the weak form, this is my original problem, okay? I'm going back to the beginning. On the left of my bar, I had a known displacement, u0. But when you do the weak form, and you integrate by parts, what happens is on the boundary, you have the stress. The stress at L, the stress at 0. And you say, right, the stress at L, I know it. But the stress at 0, I don't know it. I know the displacement. So what do I do? And I said, okay, we are going to forget this term. We are going to build the system. And when we have the system built, we are going to impose that the displacement is known at that particular point. Okay? If you remember, this is how we said we were going to do it. So let's do it. And I'm doing it with a particular case so that you can see what is going on. Right. So how do we do the Dirichlet boundary condition? So you have a bar, we have, for example, 3 points, and I'm telling you that here my displacement Q1 is known. And it could be anything. In the majority of cases, it's going to be 0, because it's going to be fixed. But let's do it general, and then you can solve any problem that you like. Is a number, alpha, one number. We know it. Okay? Now, when you assemble the system, what you have is, well, a 3 by 3 system. How do you call it? F, capital F here. A 3 by 3 system like that. This is the result of assembling the stiffness matrix on the left and the vector on the right. Agree? This is what you will get. This is nothing but writing the 3 equations for this system, which you have them here. But now you say, careful, because this guy here is known. Q1 is known, right? If Q1 is known, this one here means I'm going to cross the first equation. I don't need the first equation because the value of Q1 is known. That's what I'm saying, okay? I cannot have 3 unknowns. I cannot have a 3 by 3 system if really one of the unknowns, Q1, is not unknown as such. I have one less. So I need to get rid of one equation. Which one we get rid of? The same equation associated to the node where you actually have the data. If your data was given at the 3rd node, you would get rid of the 3rd equation. Okay? That's the first thing you do. And now you say, okay, I got 2 equations now. Do I have 2 unknowns? And I say yes, because Q1 is known. It's a number. So you multiply these two guys, and because this is known, this is a number, you move it to the right-hand side. It's known, so whatever is known, right-hand side. And that's it. All of a sudden, you have now what you wanted, a smaller system. In this case, 2 by 2, which makes sense because only two unknowns were necessary. The displacement at 2 points, not the displacement at 3. 3, 1, alpha. Okay, this is the 2 by 2 system. And now you solve this one. Now, the reason why I wanted to do it with alpha is because you can see how this is contributing to a modification to the right-hand side. Now, in solids, in solid mechanics, civil engineering, 90% of the problems will involve structures where the displacement is 0 at one part of the boundary because they are fixed. Right? If this is the case, if alpha is 0, this here is 0. Okay? So imposing a 0 boundary condition is like taking the system and not just crossing the row, also crossing the column, because there is no contribution going to the right-hand side from these guys. So you could cross row and column. That's it. You could do that. But be careful, because in other problems in civil engineering, for example, seepage flow, or in aerospace, in a lot of like things like wind tunnel, when you know velocity at certain places, they are not 0, these values. Okay, so you're going to need to modify the right-hand side. So be careful. Right, where are we? Is it clear? Okay. So here is an example. Okay, it's a very small one, but you have 3 nodes, 2 elements. I have in each element, let me switch. So you have 3 nodes here, 2 elements. The area of the cross-section is constant in each element, but is different in element number 1 and in element number 2. The Young modulus is constant in the element, but is different in element number 1 and number 2. So 2 different materials, 2 different cross-sections, 2 different lengths also for each component. And we have fixed displacement on the left and right and a point load here. Okay? So I'm not doing it this one because you have the model answer here. That's for you to go and practice and make sure that you match the answer. What I'm going to do is the ones a bit more complex that you have in the list of exercises. These will be the ones that I will solve here. For the ones that you have the model answer, try them at home. If you don't get the answer, come to see me or ask me here in the class. But what you have here is the elemental stiffness for the element 1, elemental stiffness for the element 2. You assemble, okay, the 3 by 3 matrix. And how many actual unknowns do you have in this problem? I have 3 nodes in theory, but how many real unknowns do you have? 1, 2, already heard a few answers. 3, 1, 2, or 3. Well, you cannot say more. You know, you would say another number, isn't it? Do I know the displacement on the left? Yes. Do I know the displacement on the right? Yes. So 2 of these guys are not unknowns. I have 3, but 2 of them are actually known. Only 1. Okay? So here is gonna, in the second slide, what you will see is how to go from this 3 by 3 system, crossing row number 1, row number 3, and moving to the right-hand side what is known. You end up with an equation, one unknown, which is this one here that you have in the middle. You solve it, and you obtain the displacement at the midpoint. And then, something that I particularly like, and this is why I wrote it here, you can go and compute the reaction forces. Right? The reaction at the left, the reaction at the right. Because once you know Q1, Q2, and Q3, you can compute the reactions that are on the right that were initially unknown. Right? And you can satisfy equilibrium. Not satisfy, you can verify that the solution that you got satisfies equilibrium, which is something perfect, because if you do that, you can go home very, very happy the day of the exam, because it's like checking that your answer is correct. You check the equilibrium. Right? Try it. I'm going to do a different one in the second hour, but you could try this one. Okay? So let's do a break of 10 minutes.